Animal fats and vegetable oils are the most widely occurring lipids. Chemically, both fats and oils are esters. And as we learned in chapter 15, esters consist of an alcohol portion, and that's going to be derived from glycerol. And then they also contain an acid portion, which is derived from or furnished by the fatty acid. And so a lot of times it's helpful to kind of think of it like this, where we have glycerol, which is shown here. There's one glycerol molecule, and then 3 fatty acid molecules, and these linkages here are the ester linkages. So these are all ester bonds. And I want to remind you that ester bond is just an oxygen and a C double bond O with R groups on either side. So in fats and oils, the alcohol portion is always derived from glycerol. Because that glycerol has those 3 groups, a single molecule of glycerol can be attached to 3 different acid molecules. And so here's an example of the esterification of glycerol in 3 molecules of stearic acid, and that gives us a glycerol tristearate, which is also known as a triglyceride. So the esterification results in the formation of triglycerides. So if you've had your triglycerides tested, that's what they're testing. There's another name for these, and it's triacyl glycerols. But more often, we refer to these as triglycerides. Now, the fatty acid component here, it is rarely identical. More often, it's a mixture of different triglyceride molecules. See, I'm going to say a mixture of different fatty acid molecules. Right? And so, for example, butterfat contains at least 14 different fatty acid components. So these are just all mixed in together. Now, with some exceptions, triglycerides that come from animals other than fish are solids at room temperatures and are called fats. So fats are derived from animal sources and are solids at room temperature. And then they're primarily composed of triglycerides with long chain saturated fatty acids. And if these are long chain fatty acids here, so this is an example of a fat, that's a triglyceride that's considered to be a fat. These tails here are really close together, and so that means there's an increase there in dispersion forces. And that increase in dispersion forces increases the melting point, and so that's why they're a solid at room temperature. Then oils, on the other hand, generally come from plants or fish sources. So when we say animal sources, we're not talking about fish. So oils are derived from plants and fish. They are liquids at room temperature. and are generally composed of triglycerides with unsaturated fatty acids. And so, for example, here we've got these double bonds shown here, which would be an unsaturated fatty acid. And so you can see that here these tails are much farther apart in an oil than in a fat. And so because they're much farther apart, they don't have as many dispersion forces. And so that means that they are a liquid at room temperature. So that's kind of interesting application of dispersion forces. Now, when we look and compare animal fats with vegetable oils here, and so the animal fats that we have are butter, beef, chicken, lard, and egg. One of the things we're going to notice here, right, is that they have higher melting points. And the reason that they have higher melting points is because they have more saturated fatty acids. And so this is why they end up being a fat or solid at room temperature. Now, when we look at vegetable oils, they have fewer saturated fatty acids and more unsaturated fatty acids, and so that's why they end up being a oil at room temperature and have lower melting points. So these tend to have higher melting points, and these tend to have lower melting points. Now, excessive fat in the diet is recognized as one of the risk factors influencing the development of chronic disease. And the main concern about excessive dietary fat, especially saturated fat here, centers on its role in raising blood cholesterol levels. And so high blood cholesterol is a recognized risk factor in the development of coronary heart disease, which is the leading cause of death of Americans every year. Now, that being said, there's also some genetic things that come into play there, so it's not all controlled by food, but food is one part of that. Now, let's talk a little bit about the reactions that these triglycerides can undergo. So the chemical properties of triglycerides are typical of esters and alkenes because those are the kind of two functional groups here that are present. We have esters, and then we have unsaturated molecules. We have alkenes. So they can undergo hydrolysis. It's one of the most important reactions in fats and oils. So basically what you do is you treat, right, your triglyceride with water, and then you are going to have either acid or an enzyme called lipase. Now, lipase here is found in the digestive system. Right? And this is what will help break apart fats and oils during digestion, as well as the breakdown of cellular fat deposits to supply energy begins with this lipase catalyzed hydrolysis reaction. So when this triglyceride is reacted with water and an acid or lipase, the enzyme, it breaks apart into glycerol and then the three different fatty acids that we see here in this particular chain. Another reaction that fatty acids can undergo is saponification. Saponification is also known as the process of soap making. And so what you do is you take your fatty acid and you react it with a strong base. This is a very commercially important reaction. The production here is of glycerol and then the salts of the fatty acids, and that's what are also called soaps. Now, the properties of soap depend on the base that is used. So, for example, if we have sodium salts, These are what are considered in soap making hard salts, and they're found in like cake soap or bar soap. Then you have potassium salts, which are soft salts, which are then found in soft soaps like liquid soap. In traditional soap making, animal fat is used as the source of triglycerides. And then lye is used as the NaOH, or an aqueous extract of wood ash is used as the base there. Now, something that's interesting is this was lost with the fall of Rome. So they had soap during the Roman Empire, and then we were pretty soapless between AD 500 to 1500. And so that is one of the many reasons that we had those really devastating plagues. And infant mortality was pretty high during this time as well. You can, in England at least, they can correlate the reduction of infant mortality with the increased use of soap in the 1800s, which is kind of interesting. So a lot of people think that that chemical reaction of soap and that particular molecule is one of the big molecules that changed history. Now, in Chapter 12, we learned that double bonds can be reduced to a single bond by treatment of hydrogen in the presence of a catalyst. This is a really important commercial reaction of fats and oils. They use the same hydrogenation process where some of the fatty acid double bonds are converted to single bonds. And so the result is a decrease in the degree of unsaturation and then a corresponding increase in the melting point of the fat or oil. So when this occurs, we see an increase in the melting point. So one of the places that we see this is in margarine. If there is margarine that's made from an oil, it's gone through generally a hydrogenation process, and that's why it's a solid at room temperature. Another kind of thing that goes through hydrogenation is peanut oil. In many of the peanut butter brands has been partially hydrogenated so that that oil is now a semi-solid and doesn't separate. It's also used in shortenings. Now, one of the things that's unfortunate about this is I want you to notice in the oil here, we have all cis configurations. So we have these cis bonds here. And then some of the double bonds reform as trans bonds. And this results in trans fatty acids. And trans fatty acids are interesting because they don't form that U shape anymore. So now these can get really close to each other, and that's what increases the melting point of that margarine, is those increased ability of increased dispersion forces between these molecules here. Now, the consumption of trans fatty acids raises blood cholesterol levels. Right? And the current dietary advice is to reduce the consumption of those products that contain saturated and trans fats. Now, one of the things that's interesting is you don't have to report trans fats if they're under a gram, if I remember correctly. And so some companies get away by saying they don't have any trans fats on their label by reducing their serving size. So what you have to do is you have to read on the label, and if there's any sort of hydrogenated oil, I guarantee there's trans fats in that particular food. So if you're trying to avoid trans fats, you really need to read the labels and make sure you're avoiding foods that are hydrogenated. Now, here's our reaction map for triglycerides. So we start right here. We have a triglyceride. We can react it with hydrogen and some sort of catalyst. They use nickel, but I want you to remember platinum and palladium are also used as well. And we can get a more saturated triglyceride. You can react the triglyceride with sodium hydroxide and get a glycerol plus fatty acid salts. Or you can react that triglyceride with water and an acid, and you end up with the glycerol and the fatty acids. Now, the last thing we're going to talk about in this screencast are waxes. Waxes are esters of long chain fatty acids and long chain alcohols, right? These are water, insoluble, and not easily hydrolyzed. They tend to occur as protective coatings in nature on skin, fruits, leaves, and fur. And then they're used commercially to make cosmetics, candles, ointments, and protective polishes. I want you to notice that these are also secretions from plants and animals that are a solid at room temperature. They melt at relatively low temperatures, and so that's why we end up using them with candles. They're generally really soft and malleable, and they're very, very hydrophobic, and that's why they repel the water. We've got some examples of waxes here that we find. Beeswax, for example, here's the structure of the wax. I want you to notice the two long chains on either side of the ester here. One of those chains comes from a fatty acid and the other chain comes from an alcohol. And so that's the reaction that we see. And the product here is just these long chains on either side of an ester bond. And that's the principal component of beeswax. Other waxes that occur are the Canoba palm, which is native to Brazil. It has wax deposits on its leaves to protect it from excessive water loss. Wool has a coating of lanolin, which helps shed water. And then, of course, we produce wax as well. So human earwax protects the ear canal from bacteria and other foreign substances. And so these are all examples of different waxes. In the next screencast, we're going to talk about other different types of lipids, particularly those found in biological membranes. As always, if you have any questions, please feel free to stop by my office.